All right, hello and welcome. So this is going to be one of the last lectures, probably one of the two last lectures. So what we're going to be doing today is we're going to be looking at the wave equation first. And remember that what we were doing last time around is we were trying to understand how to obtain, how to uh, construct the Green's function for our heat equation, and we saw some interesting properties and so on and so forth. And what then we essentially solve the forced heat equation. And now what we want to do is we want to start and we want to figure out how to do similar things for the wave equation. Okay, so that's the lecture. That's going to be the lecture for today. I mean, we will also go on to do some things about Poisson equations after that, but that's going to be what we start off with today. All right. So let me get to sharing screen. And also to get rid of the distraction, let me turn my video. Very good. So now, so what do we want to do first? So we want to do some Fourier transforms. Okay. So we're going to start off with the wave equation, and we're going to look at a forcing term, and f, this is going to be given at our end. This interval is, this is a given forcing term. And our wave equation, as you know very well, is del 2 phi del t2. This looks horrible, del t squared minus c squared grad squared phi is equal to this f. Okay. Now this, we are going to be subjecting this to initial conditions, and the initial conditions is going to be the following. So phi at this, at the initial time slice, this is equal to 0. We'll also say the first derivative of phi in this initial slice is also equal to 0, and we'll further restrict this to have limit of phi when x goes to infinity. We are going to go, we'll take this to be equal to 0. Now c here is the speed of the wave. If it's light, then it's just the speed of light. Okay, so we now seek a Green's function of the following form. So the Green's function has to be del 2 del t squared minus c squared grad squared acting on g x t y tau. Let's put some vectors because we're doing it say 3 dimensions. So n dimensions, n plus 1 dimensions. So this is t minus tau delta n of x minus y. Okay. Now the boundary conditions with this, as you can understand, so these are going to be similarly. So this is g of x 0, y 0. This is equal. So sorry, this is not 0. This is tau. This is equal to 0. Del t of g of x 0 y tau is equal to 0, and we have limit of mod x going to infinity g x t y tau. Sorry, is equal to 0. So the solution to the problem is again something that should be clear. So phi of xt is going to be just integral 0 to infinity, integral over all space, f of y tau, g of x t y tau, d n y d tau. Put the vector signs in. All right, so this is what we want to do. Okay, this is the formal solution to this. So we proceed as before, and we are going to Fourier transform the defining equation for the Green's function with respect to the spatial variable. Okay, so let's do that. Fourier transform. What are we going to get? So del 2 del t squared. So here we are Fourier transforming this equation. Okay. So if we do that, so g tilde of kt y tau. Remember that we are Fourier transforming only the x plus mod k squared c squared g tilde k t y tau. Always put these in the wrong places. So this is now going to be equal to what? The Fourier transform of the del n x minus y. So this is just exponential of minus I k dot y and a delta function of t minus tau. This is simple, straightforward. So again, this is subject to the condition that both g and del t of g vanish at t equal to 0. Okay. Now again, so what we'll do is we'll treat k as a parameter, and we recognize this equation as an initial value problem in the variable t. So so let's do this. So this is something that we had solved earlier when we were doing the ODEs, and the solution to this, if you go back and find this in our previous lectures, so you'll find that the solution to this when we were doing the ODEs was something of the form. So yeah, now that I say this, I realize that I have actually forgotten. I had forgotten to do a piece of one lecture. So what I'm going to be saying now may not be familiar to you. So let me actually pause this for a moment and get back to something that I should have done earlier. So let's actually, before I write down the solution to this problem, let me actually take you back to the application of application to initial value problems in ODEs. Okay. So All right, so this is going to be a detour of what we should have done earlier, but I forgot. Okay, so Green's functions can be used to solve initial value problems. And for that, let's take the independent independent variable as time, and suppose that we wish to find a solution of a function which is y, which is in some t not to infinity, that goes to r, that obeys the particular differential equation. L of y is equal to f of t. Okay, and this is subject to initial conditions y at t equal t naught is 0 and y primed at t naught is equal to 0. Okay, so the method of constructing the Green's function will be similar to what we did earlier in the case of a boundary value problem. So for this, what we want to do is we are going to solve the Green's function L of g, which is delta of t minus tau. So that for each value of tau, the Green's function is going to satisfy the homogeneous equation L of g is equal to 0 for t not equal to tau. So, okay, so what are we going to do? So we are going to, construct the general solution. So steps would be, number one, construct general solution. Of the homogeneous equation of Lg equal to 0 for t naught less than t less than tau. Okay, so this is, so g is going to be given as a y1t plus b y2t. Here y1 and y2 is any basis of linearly of the linearly independent homogeneous solutions. Okay, so that's step one. Step two, as we did before, so now we apply the initial, so not as we did before, but in sort of in contrast to what you had for the boundary value problem, we will apply both the initial conditions to the solution, right? So what is going to happen is that so apply both boundary conditions or not with boundary or initial conditions. To the solution. So what do we get? In that case, we get a of y1 t naught plus b of y2 t naught is equal to 0, and a of y1 primed t naught plus b of y2 primed t naught is equal to 0. So this essentially means that y1 t naught y2 t naught y1 primed t naught y2 prime t naught this into AB, this is equal to 0. Okay. Since y1 and y2 are independent, the Wronskian, which in this case is just a determinant of this matrix, is non-zero. Thus, the only way to impose both initial conditions is to set A equal to B equal to 0. Okay. So y1, y2 are linearly independent. So Wronskian is non-zero, and so that's the determinant of this matrix. So the only way to impose this, only way to impose initial conditions this is an I, it looks horrible, so let me rub out the initial here. Is to set A equal to B equal to 0. This implies that G of T tau is equal to 0 when T belongs to the region A to tau. Okay. Now for again for T, so that was point 2. So point 3 is when you have T greater than tau, Green's function is a general solution to the homogeneous equation. So G is again going to be some C into y1 T plus D into y2 T. Finally, what we are going to be doing is we are going to be applying the continuity and jump conditions at T equal to tau. So let's do this. So finally, what we do is we apply the continuity and jump on the Green's function at T equal to tau. So continuity, and jump at T equal to tau. So let's do this. So since G is equal to 0 for T less than tau, what we are going to get is cy1 tau plus dy2 tau is equal to 0. And we're going to get the jump, which is cy1 prime tau plus dy2 prime tau, the 1 over alpha of tau. So these determine the Green's function, which we will now solve to get y at T is equal to integral T naught to infinity G of T tau f of tau d tau. This essentially also gives us integral T naught to T G of T tau f of tau d tau, because the other part of this is going to be equal to 0. This is because, I mean, you would remember that things flip around, right? So g of just g of t tau is equal to 0 for tau greater than t. Thus, we have something which is like a, I mean, cause and effect. So this is a causality condition. So the value of y at a time t depends only on the forcing function for earlier times, right? So let me write this down. So causality condition, value of y at t depends only on the forcing function for earlier times. A tau which belongs to t naught t. Okay. So we can let's quickly look at an example. So an example, let's look at del 2y del t squared plus y is equal to some f of t, and y is y 0 equal to y prime 0 0. So these are initial conditions. Following the procedure that we have described above, what we're going to find is g of t tau is going to be given by theta of t minus tau, c tau cos of t minus tau plus t tau sine of t minus tau. Okay, where the choice of basis that we have, cos of t minus tau, sine of t minus tau, this just simplifies our analysis. So continuity means that g of tau tau equal to 0, which implies that c of tau is equal to 0 because the cos was 1, and the jump is going to imply that d of tau is equal to 1. Okay. So g of t tau, sorry, tau t tau is equal to then theta of t minus tau into sine of t minus tau. And the general solution to this equation, so what is happening is that the general solution is going to be y of t is equal to integral 0 to t sine of t minus tau f of tau deta. Okay. So that is how this is solved. Okay, so that was the part that I thought I'd done before, but I forgot. Now, what we need to do is that we need to go back to our wave equation. Okay, so again, this is an initial value problem. So this is now so this was how you solved the thing for the ODEs. But let's get back to the wave equation now again. So let's actually do something. Let's flip things around a little bit, and let's actually move this here. Okay. So so now let's look at the wave equation. So we have Fourier transform this. And what we will do is we'll treat k as this is the equation that we have after we have Fourier transform the wave equation. So now treating k as parameter, this essentially is the same as the initial value problem for the ODs. And so we've solved this for the Green's function that we've just done. So what are we going to get? So we are going to get the following. So let's write down the solution now. So g of k t y tau is equal to, just a second. Yeah, so this is given by t. Okay. Yeah, this is given by t theta of t minus tau e to the minus I k dot y sine of k c t minus tau. It's basically the same thing, just dressed up with some factors because the equation is not exactly the same. So to recover the Green's function, we need to compute the inverse Fourier transform. And in order to do that, so what we get is inverse Fourier transform. So we get g of x t y tau. Put this theta outside. Is it 2 pi to the n? Doing it in n dimensions. So Rn e to the I k dot x minus y sine of, sorry, not here, but sine of k. All right, this is getting a little messy, so let me try to just write things a little smaller. Give me a second. So there's a sine of k mod k c t minus tau by c mod k d and k. So we need to do the inverse Fourier transform. Now the form of the Green's function is going to be sensitive to the dimensions. So let's do this for n equal to 3. The case that we know and love are 3 plus 1 dimensional space types. And let's introduce polar coordinates. Okay, let's introduce polar coordinates for k, so that mod k is equal to k, and k dot x minus y is k x minus y cos theta. So once you do that, then what you have is g of x t y tau is equal to theta t minus tau. You're in 3 dimensions. This is 2 pi cube. Integral is 0 to infinity minus 1 to 1 e to the I k mod x minus y cos theta g cos theta. This is where this integral ends, and there is a sine c k t minus tau k dk. Very good. So all right, so that's that. Now, what you need to do is so this can be actually written as the following. So you can write this as theta of t minus tau into 2 pi I c x minus y. Let me write this down first and then I'll try and explain. Okay, in going from this, in going from the line here to the line here, what we have done is we have used the fact that the result of integrating over cos theta leaves us with an even function of k, and we recognize the remaining integral. So this let's put this in square brackets. So this is actually going to be the inverse Fourier transform of sine of c k t minus tau. So this is just this is the inverse Fourier transform of inverse Fourier transform of sine c t minus tau. And now what we would remember, hopefully, from Fourier transformations is that f inverse of sine of ka is actually stuff to do with delta functions, delta x plus a minus delta x minus a. So in that case, what we find is that our Green's function that we were trying to find is g is given by this x t y tau is given by theta of t minus tau by 4 pi c mod x minus y. It's a modulus times these delta functions. So delta of mod of x minus y plus c t minus tau minus delta of mod of x minus y minus c t minus tau. Okay. Now, you notice that the first delta function does not have any support in the region where the step function is actually non-zero, right? And the second, the second one, it just makes sure that so it just ensures that t minus tau is always greater than 0. So this particular theta function is actually superfluous. So you can just get rid of that, right? And you can just write this simply as g x t y tau. This is just given by minus 1 over 4 pi c x minus y to delta of mod x minus y minus c minus tau. Right, so that's that. So so this essentially ensures t minus tau is greater than 0, and this is essentially called, so this is the Green's function is called the retarded Green's function. Okay, retarded. Okay. Now you can use this Green's function to finally write down the solution to our problem. So we can write down phi of xt is equal to minus of integral 0 to infinity 1 over 4 pi c integral over all Rn f of y minus tau mod of x minus y delta of x minus y minus c t minus tau del ny t tau. So this is, so when you define, so you define c into t retarded as ct minus mod of x minus y. So if you do that, then you can redefine this as integral over 1 over 4 pi c squared integral over Rn of f of y minus, f of y to t retarded by x minus y tn y. Okay. This illustrates the fact that there is a finite propagation of speed for disturbances that obey the wave equation. The effect of okay, so the retarded time essentially illustrates the finite propagation speed for disturbances that obey the wave equation, as I said. So the effect of the forcing term at some point y is felt by the solution at a different location x only after time t minus t retarded has elapsed. This is how much time it took the disturbance to travel from y to x, and this is sort of in perfect agreement with what we had expected from other places. For example, if you remember what our discussion of the characteristics of the wave equation were, so this is sort of absolutely in tune with that. Okay. So that's what this part of the lecture was. So next time around, this was a little stretched out. I'm sorry for that, because I forgot that I'd not done something in between and at the end, in between. So this was the wave equation, and what is going to happen next time around is that we are going to see the Poisson equation. And after we look at the Poisson equation for a bit, so hopefully yeah, hopefully 2 more lectures, we should be able to wrap this up. And at the end, we're going to see the Laplace and Poisson equation, and give you a little glimpse of what something that you're familiar with from electrodynamics. But let me also get back to that. Something called the method of images that you guys know very well. But let's try and see how to fit it in this picture. So yeah, so that's it for now. But more lectures soon, and we're going to try and wrap this up in the next day or two. Okay. So thank you, and see you soon. Bye bye.